Hello, welcome back. Here we are again, and excited about what we're going to talk next, what subject we will discuss next. Well, we will talk about naming inorganic compounds, part 2. Although we have to talk a little bit more about binary compounds before we go into the ternary compounds. But before we start, I'd like to show you some live samples that I brought in and see whether you can distinguish whether we are dealing with an element, a metal or non-metal, or a compound. Let's take a closer look. What's in the picture now is a blue crystalline substance. It happens to be a compound, and most blue compounds are copper related. So this is copper sulfate. If I move this around a little bit, we will see a nice yellow powdery substance with a typical sulfur yellow color. This is sulfur. And sulfur, you can guess, has nothing of the metallic properties, so it's a typical non-metal. If we move a little downward here, we see a wonderful material that looks metallic, but it really isn't a true metal. But you could say it's a metalloid. It's silicon. Silicon that makes up your computer world. If I move a little here, downward or to the left, from my viewpoint, we see something powdery white, off-white, grayish. That's calcium. It's probably made out of bone meal, which contains a lot of calcium. Here we have carbon, black. Here we have, I don't know if you can see it very well, but powdery iron. So it's a little graphite black color, a little bit more in the gray. And here we have a lightweight metal. You guess it correctly. It is aluminum. So that's a metal. And if we move down here a little bit, and to the right, we see a nice coppery colored metal, red metal, and you're right, it is copper. So it's a metal, so we have a granulated copper and some copper wire mixed in. So these were elements that I just showed you. Let's look at some more compounds. We already saw the copper sulfate. Let's move on to the gray substance here. That is lead oxide, plumbous oxide, or lead-2 oxide. And here we have another copper salt, this one. So the beautiful turquoise blue, and that is copper chloride, cupric chloride. And here we have the green substance here is a crystalline compound, ionic compound, and that's a nickel-related compound. Nickel salts are often greenish in color. So that's nickel chloride. And here, last not least, we have something that we don't want to see so much, and that's rust. So it's a mixture of iron 2 oxide and iron 3 oxide. This typical rust red brick color. So those were some samples. I would have loved to have brought some more, but here in the studio, you don't want to see chemicals too much. So let's look at the menu today. Ternary compounds, naming ternary compounds. Remember, ternary compounds contain 3 different elements. We're going to learn about polyatomic ions like sulfate, carbonate, phosphate, nitrate, acetate, etc. the oxy acids in their salt, like carbonic acid and the carbonates, or sulfuric acid and the sulfates, the nitrates and nitric acid, and so on and so on, and some basic and acidic salts. First of all, let's finish some business here, and that is naming of binary compounds. Binary, remember, means two elements involved. Let's just call them A and B. And the numbers N and M are the various subscripts. Now, depending on what type of compound, remember we talked about it in episode 1 of the naming nomenclature chapter. Remember, the more positive, electropositive element goes up front, and the more electronegative element goes in second place. So we name the first element usually by its normal name, like calcium or sodium or potassium, if we use the IUPAC or Stark system for inorganic chemicals. If we use the Greek or Latin root, then we have to distinguish the different charges or valencies or oxidation states by using the suffix ik or us. The lesser electropositive or the more electronegative element, remember, goes in second place. And the second element has to be brought back to its stem. That means you have to drop the ending. And then you add a new ending, which is called "ide." So all binary compounds rhyme with "ide" or "tide" if you are using Tide in your laundry. But this is not supposed to be an advertisement. It just rhymes very well. Now, if we deal with an ionic substance, remember metal and nonmetal, then we are not supposed to mention the subscripts. When we use a covalent compound, then we must indicate the subscripts by their name, by the Greek prefixes like mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, from 1 to 10 respectively. Now let's look at both naming procedures here in contrast to each other. Let's first look at our ionic substances. So I'm just going to focus on these right now. Remember, the ik-us system is the traditional system. Ik means the higher oxidation state, us means the lower oxidation state. So we have two copper oxides. One is called cupric oxide. Cuprous is the Latin stem, and the ik ending means higher charged, higher oxidation state, or more electron deficient, and cuprous is the lower oxidation state, which means less electron deficient. So we have here cupric oxide with the oxidation number +2 here for copper, and cuprous oxide with the oxidation number +1 here in this compound. And you see that the formulas are thus different. How do we name the two lead oxides? The higher one is with a 4+ charged lead ion, and the lower one is the 2+ lead ion. So here it doesn't matter what numbers you have, but whatever is the higher one is considered then with the ending ik, and the lower one with the us. So there's not much choice here. It's usually two possibilities. Plumbic oxide would be the higher oxidized lead oxide, and plumbous oxide, the lower oxidized. You see also that the relative oxygen amount is different as well. So remember, you have to know the stems that led to the original symbol, like plumbum means lead, stannum is tin, cuprum is copper, and so on. Now, we have a little better system nowadays, which is defined by the IUPAC rules. It's also called the stock system. So the stock system is part of the IUPAC, but the IUPAC is not the stock system alone. Remember, it extends its naming rules also to organic chemicals. So here we have the same chemicals as above, only we're using a different naming system. So here we use the normal name that we're used to, like copper, and the different charges or oxidation states are indicated by Roman numerals, like copper 2 oxide and copper 1 oxide. Same thing as the Ik and the Us types. And the lead correspondingly would be lead 4 oxide and lead 2 oxide. So which system would you prefer? Probably the stock system. But the Ik Us is still very common. So we covered the ionic substances, and we know what to do. We'll see some examples in a minute, but let's now move over to the covalent molecules, the covalent compounds. Here we must name the subscripts in the IUPAC naming rules. But if we stick to the Ik Us system, we don't have to do that. We just say nitric or nitrous, or Ik and Us. But there are not that many examples in the covalent compounds as with the ionic compounds. But we do a wonderful example, of course, is the nitric and nitrous oxide. Other examples are not that common, so I didn't write them down here. So nitric oxide is the higher oxidation state of nitrogen, and nitrous oxide, the lower oxidation state. The oxidation state is written on top of the elementary symbol. And the higher the number, the more oxidized quasi the element is. This can mean in the real sense oxidized or just electron depleted, a relative status of more or less electron density surrounding the atom. So Ik means a higher oxidation state, Us the lower. We need these though for the naming of the acids later on. So you see this naming qualification is still very important. The IUPAC naming rules for covalent compounds is as follows. And let me take that down here a little bit. We have to mention the first name by its normal name, like nitrogen or carbon or silicon, whatever. And the second name, as we already mentioned, rhymes with tide or ends with "ide." So we say nitrogen oxide for nitric oxide. If we want to be super exact, we would have to use mono, but that's redundant. So often mono is not used unless there's this true distinction, like carbon dioxide and carbon monoxide. Here the mono is important. We don't like to have two vowels next to each other, so one is usually dropped. So we say carbon monoxide and not carbon monoxide. So it's sort of like a language. We elide the vowels. So nitrogen oxide tells you it's one nitrogen, one oxygen. And dinitrogen oxide tells you two nitrogens are involved and one oxygen. So that is laughing gas or nitrous oxide. Here we see what I just told you about, carbon monoxide and carbon dioxide. Now let's look at some examples, and we'll go through the list so you feel comfortable in naming binary compounds. So these are examples. Let's look at the first one. We have PCl3 as a formula, and the name is phosphorus trichloride. You see, it's a covalent compound, therefore we have to say tri. What about the next one? 2 phosphoruses and 3 oxygen atoms. So here we have to say diphosphorus trioxide. The next one, diphosphorus pentoxide. Remember, 2 vowels is not so nice, so we don't say pentaoxide. We just drop the A and say pentoxide. It goes better over the tongue. It's easier to pronounce and say. The next one would be N2S3. Well, you guessed it, it's dinitrogen trisulfide. Now we're coming to an ionic species, 2AlO3. So we don't say dialuminum trioxide here, no, because it's an ionic substance and we are not supposed to mention the subscripts. So we just say aluminum oxide. Now aluminum just has one charge, it's only 3 plus, so therefore we don't have to use Roman numerals. Here we have a covalent substance again with 2 sulfurs and 10 fluorides. How do we name this compound? Well, we say disulfur decafluoride. And there's a little O forgotten here, so I made a misspelling. But it should be UO-ride, fluoride. And this last compound is very interesting. It's calcium carbide. Now, we haven't heard of carbide so much. But when you look, it's an ionic compound. The calcium is 2 plus. And here is the carbide, 2 carbons connected by a triple bond in the middle with 2 lone pairs. And when you add 2 hydrogens, you have acetylene. So it's an acetylene salt almost. So that would be the Lewis dot structure. And now I think we're ready to go to the ternary compounds. Ternary, as I mentioned before, has 3 different elements involved. In inorganic chemistry, we are usually dealing with the acids, the oxyacids, which are ternary, because, for instance, here we have the specimen of carbonic acid, and this is the structural model for that acid. And what is an acid? An acid is defined, there are different definitions, but a very important one that we are using is an acid is a proton donor. What is a proton? Remember, a proton is a hydrogen ion. And a hydrogen without its electron is nothing else but a proton. So that's why we call these hydrogen ions protons. In any species that can dissociate the protons, and you need a good solvent for that, like water, is called an acid. So acids have a certain property. They have a sour taste in the mouth, as we already know. And bases, on the other hand, are proton acceptors and have sort of an alkaline, soapy taste in the mouth. If you ever get soap into your mouth, this would clarify that effect. Now, the acids can be covalent molecules. Bases are usually ionic. When we talk about the hydroxy bases, there are different types of bases. Amines are also bases. But here we're dealing with a hydroxy base. So we have a sodium ion connected to a hydroxide ion. And the hydroxide ion in itself is the strongest base, meaning the most powerful proton acceptor. So when these two react, the hydroxide ion will captivate or capture some of these protons attached, or hydrogen atoms for the moment, but will strip these hydrogens off, leaving its electron behind, and will make water molecules. So you see we get then the carbonate ion with the sodium ions, and that's called a salt. So acid plus base gives salt and water. So we call that a neutralization reaction. Here we have that again. So you see the proton donor reacts with the proton acceptor and neutralizes, they neutralize each other, and we have a salt, which is a chemical that should have no acidic or alkaline basic reactions anymore. And this is the mechanism if you want to study it. So the hydroxide ions capture the protons, and then we get a carbonate ion in the end. Now we have to show you an overview of different types of acids. This might be a little complex, but the better you study this, the more proficient you will be in chemistry. You see, you can memorize all these anions, the polyatomic ions and the cations, but if you go systematically forward, then you can save yourself a lot of rote learning. So let's look at this table. On this column here on the left, we have the name of the acid and the corresponding anion that is formed once it has exchanged protons. So the little dashes in between are filled in by whatever acid's name we're talking about. And everything else tells us how oxidized the acid is, if it's a higher oxidized state or lower oxidized state. On the right here we see the different elements that could fill in, make up the particular acid we're talking about. Monoprotic, diprotic, triprotic tells you how many protons an acid molecule can release per molecule. So carbonic acid can give up two protons, nitric acid 1, phosphoric acid 3. So you see we differentiate the acids accordingly. So monoprotic means the acid can deliver 1 proton per molecular entity, or 1 mole protons per mole molecule. Diprotic, per molecule you can give up 2 protons. Triprotic means per molecule you can give up 3 protons. There are also more than 3, like polyprotic acid, but this would carry things too far for us. And we're going from the lowest oxidation state to the highest. Now normally we zero in this range here, which gives us the normal acid. And then we take oxygen away or add onto the normal form, and then we go to lower oxidation states and higher oxidation states. And these lead to different names. Now let's start with HXO. X stands for any halogen, like chlorine. Let's just substitute X with chlorine. Then we have HClO. How would we name this now? Well, we stick to the basic rule here. Hypochlorous acid. And when we substitute the proton for metal, make a salt out of it, then that anion would be called hypochlorite. And this can be done for any halogen, like fluoride, whatever. And here we have a nitrogen-containing acid, which is not very common, but it would be called hyponitrous acid, and the salts would be hyponitrites. We don't have any of that low level for carbon, sulfur, or phosphorus-containing acids. Then the next higher oxidation state would be where you have already more oxygen involved. So they are just called us acids, like chlorous acid, nitrous acid, sulfurous acid, phosphorus acid. There's no such thing for carbon. The salts would be called now ites. We don't need the hypo anymore because it's not that low down in oxidation state. So ite is the ending for the salt anions that come from the original us acid. If there's still hydrogen involved, which can happen, we call that monohydrogen sulfide, for instance, or dihydrogen sulfide, phosphide, because phosphorus acid has a lot of hydrogens, so it can make more subspecies. The normal acids are called chloric acid, nitric acid, carbonic acid, sulfuric acid, and phosphoric acid. So these are the normal ones. And the salts are then called ates, like calcium sulfate, sodium phosphate, etc., etc. And when we have more oxygen than the normal, and that only happens for the halogen acids, then we call it per-us acid. Like it's actually coming from hyper, but we drop the high and just use the per. So perchloric acid. And I see a little mistake. So that should be ic. So perchloric acid. And the salts would be called then per-ates. Per-ates. Like perchlorate. So the salt, which is KClO4, would be called potassium perchlorate. Let's look at some examples for naming ternary compounds. Here we have sodium H or NaHCO3. That would be called sodium hydrogen carbonate. KIO. Now at first you would say, oh my goodness, what could that be called? But if you stick to the pattern, then you know it's the lowest oxidation state with just one oxygen. And remember, then we say hypo. Hypo means less than. And ite, the ending. So potassium hypoiodite. And here we have a compound that might not be so easy from the start, but we say aluminum. Remember, the first element is mentioned by its normal name, and then this is the polyatomic ion. Remember, it comes from phosphate, has O4, that's the normal, but we still have hydrogen in there, so we have to say aluminum dihydrogen phosphate, and here we are finished with that name. Then we have lead nitrate. According to the stock system, this would be lead 4 nitrate. And here we have tin 2 chloride. Remember, the normal one was chlorate, ClO3. Just remember the normal types. It can have maybe sometimes 3 oxygens or 4 oxygens. So these you just have to memorize, and then you can just take oxygens away or add on, and the names will be then accordingly. So this is tin 2 chloride. So we covered that already, but before we end, I like to talk a little bit about the bases, the naming of the bases, because they're also ternary compounds. Why? Because they have usually a metal here, an oxygen, and a hydrogen. So 3 elements. The first name is the regular name, and OH is called hydroxide. Remember, I'm saying here names of hydroxide bases because there are also other bases. Now, the bases are all proton acceptors, as you know. So here we have some names, sodium hydroxide. And this is a very important cation, the polyatomic cation, which is called ammonium. And ammonium is what we call a pseudo-alkaline metal, just like the cyanide ion was a pseudo or pretending halogen element. This is calcium hydroxide. Remember, we don't mention any subscripts when we have ionic species. And this is the hydroxide ion. And before we stop, we have a few organic acids that are often involved, formic, acetic, and oxalic acids. And the salts are 8s. This is a lot of stuff, and I hope you won't have trouble learning this. But remember, it's very systematic, and see you next time.